Hello everyone. My name is Chusin Y, and I am presenting our work titled Scalable Feature Matching via State Space Modeling and Sparse Correlation. This is a joint work with Associate Professor Bo Lee from Northwestern Polytechnical University. In this work, we propose SLIM, which stands for Salient Lightweight Matching, an efficient and scalable semi-dense feature matching method designed for high-resolution image matching. First, I will briefly introduce the motivation of this work. Image matching is a fundamental problem in computer vision. Its goal is to establish correspondences between two or more images with overlapping fields of view. It is a core component in many important applications, such as SLAM, visual localization, and novel view synthesis. It is also widely used in areas like autonomous driving, medical imaging, and remote sensing. Because of this broad impact, improving image matching efficiency and scalability is highly valuable in practice. In recent years, detector-free and semi-dense matching methods have achieved strong accuracy. However, many of them still suffer from three important limitations. First, they rely on heavy correlation computation, which leads to high latency and memory usage, especially at high resolutions. Second, many methods use attention-based context modeling, which also becomes expensive as the image size grows. Third, expectation-based coordinate regression at the fine stage may limit localization accuracy. So the key question is, can we design a feature matcher that remains accurate, but is also much more efficient and scalable? To address this problem, we propose SLIM, a scalable feature matching method that delivers reliable matches with low memory footprint and low latency. Our method has three key components. The first is a lightweight network design based on a hybrid convolution Mamba backbone. The second is sparse correlation via norm-based feature filtering, which reduces redundant matching cost. And the third is a recurrent coordinate refinement module, which improves localization accuracy. Overall, SLIM is designed to achieve three goals at the same time: high accuracy, low memory footprint, and fast inference. This gives us a stronger accuracy efficiency trade-off than prior semi-dense matchers, especially for high-resolution inputs. Next, I will introduce the main method. We first extract multi-scale features using a hybrid convolution Mamba encoder. The backbone follows a three-layer architecture. Here, convolution next blocks preserve local image details, while SSTD-based Mamba blocks enable efficient cross-view context fusion with linear complexity. At the end, we use an FPN to fuse deep semantic information with shallow spatial details, producing robust multi-scale feature representations for matching. So this part gives us efficient feature extraction while still preserving both local detail and global context. After feature extraction, we perform matching using a dual-stage sparse correlation strategy. The key idea here is to use the L2 norm of feature vectors as a saliency prior. Instead of computing dense global correlation everywhere, we only compute correlation on high-known features, which are more likely to be informative and reliable. This significantly reduces redundant computation at the coarse stage. Then, starting from these coarse matches, we perform local window correlation at a finer scale to obtain more accurate correspondences. So this module improves efficiency mainly by replacing expensive full correlation with saliency-guided sparse correlation. Finally, for subpixel localization, we introduce a recurrent refinement unit, or RRU. Instead of using expectation-based regression directly, we reformulate refinement as an iterative coordinate optimization process, inspired by recurrent optical flow estimation. This module is lightweight with only about 816,000 parameters and achieves accurate localization in just 3 to 5 iterations while maintaining real minus time performance. For training, we supervise the model with three losses: a coarse matching loss, a fine matching loss, and a refinement loss. Next, I will briefly present the experimental results. We first evaluate relative pose estimation on megadepth and scannet. On megadepth, SLIM achieves 57.9 you see at 5 degrees, outperforming efficient loft-her while using only 5.9 million parameters. On scannet, our method also achieves competitive performance with strong efficiency. These results show that SLIM provides a very favorable balance between accuracy and runtime across both outdoor and indoor benchmarks. We also evaluate homography estimation on each patches. Here, SLIM achieves 69.4, 78.2, and 86.3 AUC at 3, 5, and 10 pixels, respectively, which establishes strong state-of-the-art performance among the compared semi-dense methods. we further compare with dense matches. Although some dense methods can achieve stronger absolute accuracy, they usually require much heavier models, more computation, and more diverse training data. In contrast, Slim remains much more efficient while still delivering competitive results. Finally, we evaluate resolution scaling. This is one of the most important results of our paper. As the input resolution increases, Slim scales much more gracefully than prior methods. At 1200 by 1200 resolution, it uses 45% less memory than GML, and it is about 1.8 times faster than efficient Lofter while maintaining strong matching accuracy. Here we show some qualitative demo videos for both indoor and outdoor scenes. These examples illustrate that Slim can produce dense and stable correspondences in challenging real-world scenarios, while still keeping the computation efficient. Now I will conclude this presentation. In conclusion, we presented Slim, an efficient and scalable semi-dense feature matching method. By combining a convolution Mamba hybrid backbone, L2-norm-guided sparse correlation, and lightweight recurrent refinement, our method reduces redundant computation while preserving salient features and strong matching accuracy. Across multiple benchmarks, Slim achieves a strong accuracy-efficiency trade-off, especially for high-resolution matching and resource-constrained applications. There are still some limitations. For example, the training-free norm filtering may drop useful low-norm features in difficult cases, and the recurrent refinement can be sensitive to some hyperparadigms. In the future, we plan to improve the robustness of norm filtering, further optimize the refinement module, and scale the model with more diverse pre-training data. Thank you very much for your attention.